In this video, we'll talk about different types of solids, liquid, gases, and then intermolecular forces or interparticle forces, same thing. So I'm going to start by talking about ionic solids. As you know, ionic is made up of a metal and a nonmetal. And we're going to talk about how those positive and negative ions, the metal would be the positive ion, the nonmetal would be negative, unless it's hydrogen, is how they are held together. So ionic compounds have two different things holding them together, or two different factors of their solid state. One of them is that the positive and negatives will always be surrounding each other. And you can see here in this little box, the negatives are bigger and the positives are smaller, and that's always going to be the way they're represented. Positive ions are always going to be the smaller of the two. So you can see that we always have a positive next to or surrounded by a bunch of negatives. Positive and a bunch of negatives. You'll also see that they pack as close as they can. So there are two things going on. One is the attraction between the positive and negatives, and then also there's going to be the way they are arranged, the way they are packed together. So we're going to talk a little bit about something called lattice energy. And here you can see Coulomb's law again. It's always there, popping up. So lattice energy is a positive enthalpy change that accompanies a separation of a solid ionic compound. So if we separate NaCl into sodium and chlorine, we would need to use the lattice energy. We can use lattice energy to figure out how strong the ionic forces are, how strong those attractions between the positive and negative here. So we can use Coulomb's law, and then here you'll see F lattice, so lattice energy, lattice force. We have our constant that we don't really care that much about, and then we have the Q, the charge of the cation and the anion, and the distance on the bottom between the two. So the two factors that will affect the lattice energy are the magnitude. Okay, so if you have 3 plus and 3 minus, it's going to be stronger than 1 plus and 1 minus. And then the ionic radius, or how far apart those ions are, The smaller ions are going to be able to pack more closely. So they are going to have a smaller d, which means the lattice energy will be higher. So here are some examples of lattice energy. Okay, so here in the red box, you can see they are all Li, and they're combined with a 1 minus charge. They're all halogens. So here, the Q are going to be the same, but D is going to increase because as you go down a group, so down the halogens here, our atoms get bigger. So our ions would get bigger as well. We would have more of a distance. So if the distance goes up, the lattice energy goes down. So you can see as our halogens get bigger, our lattice energy is going down. The green boxes are showing the opposite, okay? They are similarly sized ions. There's not that much difference between sodium and magnesium. They're right next to each other. And there's not that much difference between fluoride and oxide. They're right next to each other. So we can kind of say D is essentially constant, not perfectly constant, but it's close enough for us to compare what happens with just the charges. Here we have plus 1 minus 1, and here we have plus 2 minus 2. So you can see as the charge gets bigger with our plus 2 minus 2, the lattice energy gets stronger. So lattice energy, again, is a great way to compare the strength of our ionic forces. So now we're going to move into covalent compounds. And one of our solids there is going to be a network covalent solid. Okay. It is a molecular solid, but it has a high melting point. And that is because it is a web. Okay. It's not a network covalent, you can think of as kind of like a grid. Okay, so it's kind of like there's a lot keeping it together. The list of network covalent solids that you should memorize are carbon, silicon dioxide, silicon carbide, and silicon itself. So it's pretty easy to remember, okay? And then carbon will be broken up into diamonds and graphite. And then silicon dioxide is quartz and glass. So pretty easy to remember and definitely important to remember. So let's take a look at what those network covalent solids look like. In diamond, atoms are bonded 4 times. So each atom has 4 bonds. There's one you can't really see here, but there are 4 for each one. Okay, so each one is bonded 4 times. Very high melting point, very strong bonds. For graphite, there are different ways that graphite can be bonded, but there's 3 bonds. So what happens is the 3 bonds, and then there's different layers, okay? They're not quite as strong as diamond, but they're still pretty strong. Because there are layers and there's not really bonding between the layers, well, they're loosely bonded, because it's not as strong as a diamond bond where there's 4 full covalent bonds, the layers can peel off more easily, and that's why you'll see that used for pencils and stuff like that, okay? These 2 over here, the buckyball and the nanotube, are just different ways that carbon can be bonded. You'll see those a lot. That's definitely something you would talk about in more advanced courses. For right now, we're just trying to figure out how these network covalent solids operate. So diamond is not going to peel off as much because of that bond between the layers, where graphite, because the bond is much looser between the layers, they will peel off. So here's silicon dioxide, quartz, and glass. You can see the difference. So the difference between what we're talking about now, where they're network covalent solids, and the IPFs that we're going to talk about in just a few minutes, is that here they are actually bonded. These are actual bonds, okay? And they're actual bonds, not just attraction. So when they're actually bonded, that's a network covalent solid. When there's just attraction, that is just an IPF. So this is a review. We've talked about this before, but I just want to quickly throw this in here. We're at the review stage of the year anyway. So we have talked about allies before. I'm going to quickly go over that because you'll see that a lot on these questions on this particular topic as well. So metallic bonding, we have talked about before. What will be is just cations, positive ions, surrounded by what we call delocalized electrons. Those are electrons that come from the metal atom and then can move very easily. Alloys are mixtures that contain at least one metal, and they do so to improve the properties that we're going to use alloys to build things. As you might remember from a video not too long ago, there are 2 types. Substitutional is when you have a pattern here, and then you put one metal in place of another metal atom. The interstitial is when you have the pattern, and you'll notice none of those red balls are replaced, but you'll have the other metal atom in between them. And if you remember from the last time we did alloys, this one happens when the metals are close in size, and this one happens when they have very different sizes. So that's what we're going to talk about for solids. And now we're going to move on to the main topic of this video, which is interparticle forces. You'll often hear this called intermolecular forces or IMF. On AP, they probably will say that. but it's more specifically known as interparticle forces because it doesn't need to be a molecule. It can be an atom as well. So these are the major forces that we will be talking about, the major categories. London dispersion forces, which you'll also hear referred to as LDF or sometimes van der Waals. They are between all molecules. You will always have them. However, it is the only force if your molecule is non-polar. And we're going to talk about what that means today. Hopefully you remember that from your first year chem course, but if not, we're going to go over it today. Dipole-dipole forces are when it is polar, and hydrogen bonding is extra special polar. And then ion dipole are between ions and polar molecules. So this is what the ion dipole forces are, what's happening when something dissolves in water. The ions are breaking apart, they're dissociating into water. Water is a polar molecule. So we're going to talk about LDF first. LDF comes from what we say polarizability of atoms or electron clouds. So when we think of atoms, we tend to think of them as balls, but there are these amorphous clouds, meaning the clouds can go all around. So at one point, if you see this as electrons, this is where the most electrons are at this one split second. And this is another one. You can see that they're going to be more dense in one area and then more dense over here, okay? So the polarizability of electron clouds is where LDF comes from. When they are in this type of picture, these electrons are going to have our slightly negative charge. That's the symbol for slightly negative. And then this side is going to be slightly positive because it has fewer electrons. Now that doesn't last. It's not a dipole, which we'll talk about in just a second, but because electrons are constantly moving, we do have this slight negative and slight positive. And then over here, we'll have slight negative where it's dense and slight positive where it's not. Slight negative where it's dense, slight positive when it's not, okay? Because this is happening, our slight positives and slight negatives can attract each other, and that's what the LDF will be. You'll have this attraction even in molecules that are nonpolar, or even in atoms, because these electron clouds are moving constantly. We do have these split second slight positive and slight negative. So here we have a temporary dipole. You can think of it that way. And then they will be attracted to each other. So if there's a temporary dipole in one molecule, like we can see here, and then another one here, those positives will attract the negatives, and then vice versa, okay? So factors that will affect your LDF is larger size is going to have a stronger LDF because it has a larger electron cloud. And then if you have a longer, straighter chain, okay, and we're going to talk a little bit about that as we go through this video. We have some organic molecules that are very long carbon-hydrogen chains that also will have oxygen thrown in there. The longer and straighter they are, the more LDF there will be. So if we take a look, all of these compounds are nonpolar molecules, okay? So they only are going to have LDF. And you can see that the boiling point decreases as the size of the molecule decreases, and that's because the LDF will be weaker. It's less polarizable if it's smaller. So the bigger the molecule, the more LDF you're going to have, the higher the boiling point will be. The smaller the molecule, the lower LDF you have, so the lower the boiling point will be. Melting point and boiling point are just the energy you need to overcome any interparticle forces. Okay, so the stronger the interparticle forces, the higher the boiling point or melting point will be. The lower the interparticle forces, the weaker, I should say, the interparticle forces, the lower the boiling point and melting point will be. So that's where this comes from. If we have less LDF, we have a lower boiling point. More LDF, higher boiling point. And the same goes when you're comparing different types of IPFs. So LDF is the weakest force we have oftentimes. But so then if something has dipole-dipole forces, it's going to have a higher boiling point than something with just LDF. So you'll see that. And hydrogen bonding especially makes a huge difference. So you would say here, which molecule do you expect to have a higher boiling temperature? Okay, now both of these are just atoms. They're just noble gases. So we would just expect LDF. There's no reason for polarity or anything like that. So we would say krypton is going to have the higher boiling temperature because it's the bigger atom. As we go down the group of noble gases, the atoms will get bigger. Krypton has a bigger atom, so it's more polarizable. It's more polarizable because it has more electrons, bigger electron cloud, stronger LDF. And if you look up the values for boiling point, you will see that krypton has a higher boiling point. It is negative 153 degrees Celsius, where neon is negative 246 degrees Celsius. So here, let's take a look at some halogens, okay? These are the boiling temperatures. So what makes I2 a solid and Cl2 a gas? It has, and these again are non-polar molecules, so we're only looking at LDF. But as you get bigger, LDF gets stronger because of that polarizability. So we know that iodine has a much bigger size than chlorine, to go to this question. So that means it's more polarizable. LDF is going to be stronger in iodine. We're going to need more energy to overcome those interparticle forces. So the more energy you need, the higher boiling point you will have. So now let's move on to the next interparticle force, which is dipole-dipole forces. A dipole or a dipole moment happens in a polar molecule. A polar molecule is not fully positive and fully negative. It's not an ion. It's a covalent molecule that, because of electronegativity differences, has a polar end, it has a positive end and a negative end. Now we say just slightly positive and slightly negative because they are not full positive and full negative like ions. So polarity is the result of uneven sharing. So you can see, here's a nice graphic that shows you the difference. Ionic, they're totally separate. They are not shared. The negative ion takes the electrons, the positive ion gives the electrons. Polar covalent, slightly negative because one electron is going to pull electrons towards itself more. That's the more electronegative. And then the other side is going to be slightly positive. If they have the same electronegativity, they are nonpolar. They share electrons equally. So you don't have that slight negative and slight positive. Over here is a chart that shows you the electronegativity values of different elements. Okay, it only shows you the non-metals because we're talking about covalent compounds here. So you can see that the noble gases don't have electronegativity values at the top because they don't bond, but the bottom ones will bond, so you'll see that. Fluorine gets a value of 4. It's the most electronegative element. And then the other ones you can see here. So a non-polar bond is going to be something that has the same electronegativity value on both sides of the bond. If it is the same element, they share they share electrons perfectly equally. They are a non-polar bond. A polar bond is between two different atoms with different electronegativity. The electrons are then shared unevenly, and the bond is polar. The more electronegative atom, which you can use your trends to figure that out, will have a greater electron density and have the partial negative charged. So you can symbolize it with two ways. One is our partial positive, partial negative way. And then you also can have this arrow showing the direction of the electrons. So the arrow will point in the direction of the more electronegative element, and then you'll make a plus sign on the less electronegative element to show that it is positive. So you'll often see dipole moments drawn this way. So polarity is a continuum based on the electronegativity values, okay? So if you have the same element, you have the same exact electronegativity value, it's going to be completely nonpolar. If you have something that's pretty close, like if you look at nitrogen is 3 and chlorine is 3, they're close. I mean, they're essentially the same. Or carbon is 2.5 and hydrogen is 2.1. They're very, very close, okay? So those are going to be essentially nonpolar. Then we have slightly polar when we have Br and O. Okay, they're 3.5 and 2.8. That's definitely going to be polar, but it's not going to be as polar as hydrogen and oxygen, for example, 2.1 and 3.5. Okay, that's going to be very polar. You are not going to be expected to say, okay, well, this is essentially nonpolar and this is very polar. There's not like a category or a number cutoff for that at all. This will show up mostly in types of questions where they say, explain the trend and boiling points here. Okay, so like if you said explain the trend and boiling points and two were close, but they would both be polar, you could say, well, this one's probably not as polar, and polarity is a continuum. So that's just information that you need to have, because if they ask you to explain something that doesn't look like it follows the trend you would expect, you need to have that information so that you can go into your brain, figure out your chemistry, and use that to explain. So we'll talk about hydrogen halogen. So over here are the electronegativity values for hydrogen and all of the halogens. Hydrogen has a very low electronegativity value. It's 2.1. So you can see that the dipole moment, which is, I've used that phrase quite a bit, it has to do with the polarity. For HF, there's a huge difference between hydrogen and fluorine. So the dipole moment is 1.82. And then you can see as we get down to iodine, which is not that electronegative, the difference is not there. It's not very strong. The difference is only 0.4. So the dipole moment is not that big. It's not as electronegative. So some polarity examples. If you draw the Lewis structure, now what you really want to have to figure out polarity is the shape, okay? And we're going to talk about that as we go through, okay? So if you draw the Lewis structure for CO2, we've done this plenty of times. It looks like this. If we figure out the shape, that is linear. So now we are talking about two polar bonds. This CO bond is polar, and this CO bond is polar, but they're polar in the opposite directions. If you were to draw the dipole moments, they would look like this. So what happens if a molecule is perfectly symmetrical, the dipole moments will cancel out. And we say, this is a nonpolar molecule. It's made up of polar bonds, but since they're polar in opposite directions, it is nonpolar overall. So the next one, SO2, the Lewis structure looks like this. And this is why it's important to think about the shape and not just the Lewis structure, because this looks symmetrical, but you know that because of this right here, it is actually a bench shape. So when we look at the shape, it would look like this. because of that lone pair up at the top pulling them down. Because in a bent shape, the dipole moments are going to not cancel each other out. This is going to be polar. There's going to be an overall positive charge, a slightly positive charge on the S, and overall slightly negative charge on the O. Next we have OH2, which is H2O. It's water. And again, that looks symmetrical, but you know because of those two lone pairs, this is 4 electron groups around the central atom, 2 of them are lone pairs, which means it is bent. And you've probably seen many times water written like this. So again, because it's bent, it is polar. So it's important to think about not only the Lewis structure, but also the shape when you're talking about polarity. Let's talk about some shapes that aren't necessarily as obvious as linear versus bent. It's very easy to see that what's symmetrical and what's not. So for CF4, our Lewis structure would look like this, and we would know that is tetrahedral. Now, if we draw that, it's hard to see, but if I was to ask you what the bond angle is in a tetrahedral, you would say it's 109.5 because they are all the same. So what ends up happening is it is a symmetrical shape, tetrahedral, so we say it is nonpolar. All of those dipole moments will cancel each other out. It's harder to see because they're not directly opposed to each other like they are in linear, but that's definitely what happens. If something is a symmetrical shape, it is nonpolar. However, if we change 2 of those F's to H's, now our Lewis structure looks symmetrical, but because this is a different shape, those dipole moments are now no longer going to cancel each other out. Even though the Lewis structure looks like it should be symmetrical and they should cancel each other out, the 109.5 degrees does not, since they're all different terminal atoms, it does not cancel each other out. So this one would be polar. Okay, so you need to think, first, will the dipole moments cancel? 2, are all the terminal atoms the same? So if the angles are all the same and the terminal atoms are the same, then it's nonpolar. If either one of those things is not true, you need to dig a little deeper and see. So for some of the more complicated shapes, like the ones with 5 or 6 electron groups, they will be nonpolar if the terminal atoms are all the same, even though not all the angles are the same because they do cancel out. So you have to really think about, okay, are they going to cancel out? Are they not? You have to actually work through that. So now that we've talked about polarity, let's go on to dipole-dipole forces. Dipole-dipole forces happen whenever something is polar. So we just said this one is polar, and this one is nonpolar. Because this is bent, and this is linear. The lower temperature is going to be the one with the lower forces, the weaker forces. They both have LDF, and we could analyze size and all of that, but we actually don't have to. We don't have to go into that because only SO2 has dipole-dipole, and dipole-dipole is stronger than LDF. So we say SO2 is going to have the higher boiling temperature because it has the stronger IPF, interparticle forces. CO2 only has LDF because it's nonpolar, so it's going to have the lower temperature. So something that has dipole-dipole will beat out something that has only LDF. Now, of course, there are exceptions to that. And if you see those exceptions, it's going to be a situation where they're saying, okay, explain this discrepancy. Explain why this is different than what you would expect. And then you would go back and say, well, if it's a really big molecule, it has stronger LDF, et cetera, et cetera. So you just have to use your reasoning. But for the most part, and if you were asked a question like this, what boils at a lower temperature, you would say the one with LDF is stronger, higher temperature. I mean, the one with dipole-dipole is stronger, high temperature. So the other one would be the lower temperature. So hydrogen bonding is just really intense dipole-dipole. So what it is a hydrogen that's attached to oxygen, nitrogen, or fluorine. And then the electronegative atom, either oxygen, nitrogen, or fluorine, on the other molecule. So a hydrogen bond is not a bond, okay? That's very important for you to know. It doesn't have hydrogen bonding. It does hydrogen bonding. It does attraction, okay? It attracts something else through a hydrogen bond. It's not like covalent or ionic bonding. And so it's really important that you don't say like, oh, H2O has hydrogen bonding. It doesn't. It has covalent bonds. But it does hydrogen bonding because it has that IPF. So what they're saying is that you need to have a hydrogen attached to an oxygen in one molecule, and then that's going to attract the electronegative element in the other molecule. So here, it's because oxygen is so much more electronegative than hydrogen. Nitrogen is so much more electronegative than hydrogen. And of course, fluorine is so much more electronegative than hydrogen, because hydrogen is over there. It has a very low electronegativity value. So when it's bonded to oxygen, nitrogen, and fluorine, it has even more dipole-dipole. So we still say that this is the negative side and slightly negative, and this is slightly positive. We're still going to say that, but it's more slightly negative and slightly positive because oxygen takes so much more of those electrons, or nitrogen or fluorine takes so much more of those electrons, right? Because they're so electronegative compared to hydrogen. So the idea and the science behind hydrogen bonding is just like dipole-dipole, except it's like more intense. Okay, so it's stronger dipole-dipole. Now, the hydrogen bonding is important because it actually accounts for a lot of what we see in the world, especially since water has hydrogen bonding. So one of the things you will see is that if you look at trends, an atom that has hydrogen bonding has a much higher boiling point and melting point than something that doesn't have it, much higher than you would expect, okay? So when you're talking about IPF strengths, when you're asked a question, this is kind of the summary of what you should do. So obviously read the question, answer the question. And then, is the substance ionic? If it is, talk about Coulomb's law. More charges, higher attraction, less distance, higher attraction. That's what we talked about at the beginning. If it's network covalent, then only talk about covalent bonding. So if it's and those network covalent that you had to memorize, only talk about covalent bonding. You don't talk about IPFs. If it is molecular, so not network, but is covalent, so molecular covalent, you'll sometimes hear. Then you talk about LDF, dipole-dipole, hydrogen bonding, okay? You'll also notice that I put a little note here, do not reference molar mass. That's not what you want to talk about. Instead, you want to talk about atomic size. Seems silly because they're so related, but you want to be very specific when you're answering these types of questions. So we're not going to say because it has a higher molar mass, because really that has nothing to do with the polarizability. It has to do with the electron cloud. The bigger electron cloud, the more polarizable it is, the stronger the LDF. Okay, so let's take a look at some questions that you might have on this types of topic. So here, what type of intermolecular forces exist in dimethyl ether? Now you'll see when you're asked for an organic compound, it might be written in this expanded formula, and that's to help you draw a Lewis structure. So you can also see that we could obviously write it as C2H6O, and sometimes you might see that, but that's usually when you don't have to write a Lewis structure. So they'll help you with this, and that means that you write it in that order. So dimethyl ether, which is an organic compound, looks like this. And that's important, because if you didn't draw out the Lewis structure, or you didn't know how to draw out the Lewis structure, you might think, oh, look, I have hydrogen and oxygen, so maybe I have hydrogen bonding. And that's not true, because when you look at the structure, that oxygen, which I guess to be accurate, I should put the lone pairs, but that oxygen is connected to carbon on both sides. It's not connected to hydrogen, so you need to think about that more. So the answer to this is going to be dipole-dipole, because it's definitely polar, and London dispersion, because that's always there. But there is no hydrogen bonding here, because in order for there to be hydrogen bonding, the hydrogen needs to be connected to oxygen, nitrogen, or fluorine. Connected to carbon doesn't do anything. So now let's take a look at C2H5OH. Looks like this. And this is going to have all of the forces, dipole-dipole, London dispersion, and this time we do have oxygen bound to a hydrogen, or hydrogen bound to an oxygen to be more specific, so we will have hydrogen bonding. Okay, and that is the same, almost the same form. Yeah, it is the same formula as dimethyl ether, but ethanol looks like this, and you know that from these silly little formulas they give you. All right, so here is two alcohols with their Lewis structures done out for you, okay, because this is the condensed formula over here, so the Lewis structures are written. And you can see one of them, propyl alcohol, has the OH at the very end. Isopropyl alcohol has the OH in the middle. So what you can see here is that although they have the same chemical formula, there is a different shape. So this is a straight chain, and this is not. Okay, it has a straight chain, but then it has a little branch off of it. So because the oxygen in isopropyl is branched, it's somewhat blocked. So it's somewhat blocked by this carbon right here, and the hydrogen, like it's in the hydrogens over here. There's just not as easy access to that oxygen. But in the straight chain, there definitely is. There's easier access to that oxygen. So that means the stronger IPFs are going to be this one right here, because it's easier for the hydrogen bonding to happen. So we would say stronger IPFs for propyl, and that is why the boiling point is not so much higher, but it is higher. You can see that. Stronger IPFs, higher boiling point. So this is the type of question when they say justify the difference in the boiling temperatures here. And you might want to think about it, okay? So here is a perfect example of what I was talking about before. They are telling you the boiling points. And if they hadn't done that and you just got the structures, you might think, oh, this one is going to be higher because of that OH. Doesn't that mean it's dipole-dipole and hydrogen bonding? But they're not telling you that. They're telling you what the boiling points are, and they're saying this one is the higher one. So why? That is the type of question you would be asked if you're like looking for a discrepancy from what you would expect, okay? You wouldn't be given these two structures and be expected to know that octane is the higher boiling point. But if they give you the boiling point, you are expected to be able to explain why. So despite the fact that propanol has hydrogen bonding, octane is so long and straight chain, it has very high LTF. And that is what you should say, okay? Again, you wouldn't be expected to know that, but if they tell you that, you have to be able to tell them the explanation. So let's take a look at what properties are affected by intermolecular forces, okay? And we know some of these already. Boiling point, vapor pressure. Some of them you might not necessarily know for sure, but you definitely, hydrogen bonding because it has water, because water has hydrogen bonding. A lot of these will be affected by intermolecular forces, like solubility. Have you ever heard the phrase like dissolves like? Polar substances will dissolve in water because water is polar. Viscosity, surface tension. Surface tension gives like a film because water molecules, because of hydrogen bonding, are very sticky to each other. Okay, so you will see here, high vapor pressure is going to be low IPS, but everything else has to do with high IPS. So you have to remember vapor pressure is the opposite, low IPS. And that makes sense because it's easier to boil something with low IPS, so it's going to have a higher vapor pressure. So now we're going to take a look at different structures. Because remember I mentioned that some of them are going to be different, like some of the more complicated structures are going to be non-polar. Okay, so you can go through and write down what these structures are. This one is going to be square planar. H2S would be bent. CO2 is linear. BRF3 is T-shaped. And PCl5 is trigonal bipyramid. So the dipole-dipole forces will show up for sure in anything that's bent, and also T-shaped. Square planar is going to be non-polar. Linear, we already know, is non-polar. And trigonal bipyramid is non-polar. So now this is another type of question you might be asked. Of which of the following pure substances, which one has the highest melting point? Okay, so you go through and use that slide that said how to justify IPFs or something like that. Use that part to do this, okay? So CO2 is molecular covalent, and that is so then you go to your IPFs. So that is just going to have LDF. I2, same thing, molecular covalent. C6H6 is LDF. And H2O is molecular covalent. It's LDF and dipole-dipole and hydrogen bonding. But graphite is network covalent. So if we didn't have graphite there, we would pick H2O. But because we do have graphite, graphite is going to be the winner here. It's going to have the highest melting point because those are all bonds, and bonds are going to be stronger than IPF because IPF is just attraction. Even hydrogen bonds with that weird name, it's just attraction. Bonds are just attraction. Anything that is, IPFs are just attraction. Anything that is an actual bond is going to be stronger. So since network covalent has bonds in between everything, it's that grid, it's going to win. It's going to have the highest melting point or boiling point. Okay, so now we have a list that we're going to put in order. So what I'm going to do is go through and list again what they have. MgO is ionic. CO2, we just said, only has LDF. This SiO2 we know is network covalent because we memorized that. O2 is just LDF. H2O is, I'm just going to write hydrogen bonding, even though it has dipole-dipole too, because we'll go with the strongest one. And then NaCl is ionic. Okay, so if we start with the weakest, we're going to have LDF. And then if you look at the atomic radius, O2 is smaller than CO2. So CO2 is more polarizable. So we would put O2 first, CO2. So that takes care of these two. Between hydrogen bonding and ionic, hydrogen bonding is next. So then we would put water. And then we have ionic versus network covalent. Now, technically, if you look up the actual numbers for this, network covalent will go in between these two ionic compounds, but that's not necessarily something you would be expected to know. So they would probably give you more information to decide between network covalent and ionic. So you would have to have more information. You would have to be given the boiling point or something like that. So I will tell you that it would be NaCl and then SiO2 and then MgO. But again, they wouldn't expect you to know that this one goes in between them. They would expect you to know that NaCl is less than MgO. Why is that? We already talked about that. Sodium and magnesium are similar sizes. Chlorine and oxygen are similar sizes, but MgO has 2 plus, 2 minus. So it's going to be higher according to Coulomb's law. Okay, so you would be expected to tell the difference there, but if you put SiO2 here or here, that would be fine as long as you had everything else in the correct order. So for vapor pressure, remember, we're talking about the lower IPFs. So here we would have dipole-dipole. Here we just have LDF. Here we just have LDF. And here we just have LDF. So we can automatically get rid of this because NH3 is polar, so it's not going to be there. And then you're going to take a look at what you would expect to be the least polarizable, because the increasing vapor pressure, higher vapor pressure means lower LDFs. So you would want to take the least polarizable. CH4 has 5 atoms, so you wouldn't pick that one. Br2 and I2 only have 2 atoms each. I2 is below Br on the periodic table, so that one's going to be bigger and more polarizable. So our answer here would be Br2. Okay, here are 2 isomers. One of them is a cis isomer, so Cl is on the same side. And one of them is a trans isomer, because Cl is opposed to each other. And the question is, what boils at the lower temperature? We would pick the trans isomer, because that trans isomer is going to cancel out those dipole moments because they're opposite to each other. And so since we cancel them out, we would just pick LDF. It's a nonpolar molecule. So we would say the trans isomer version is going to be the lower boiling point. So we've talked about boiling point. It also affects melting points, okay? So if something, here we have lowest to highest boiling temperature. So we would expect this to be, A would be first, and then B, and then C, because this would just be LDF, benzene. Toluene would have, hopefully you remember this benzene ring from a prior video. That's what this is. And then toluene would have dipole-dipole, and then phenol would also have hydrogen bonding. But for melting point, we would have this. And here is why. So you can read through that and it will tell you why the melting point is slightly different.